Okay, good morning, good afternoon, good evening. I'm not really sure what time you're watching this, all right? The purpose of this video is yesterday I tried to do a basic turbine review for my class and to record it at the same time. Unfortunately, I was online at the time, and when students joined in, it blocked the screen. So I'm going to try this and put that out on a post to see how that works, all right? So this is going to be just a quick 15-20 minute overall review, all right? So this is a turbojet engine, all right? A turbojet engine, the compressor and the turbine are on the same shaft, so all components rotate at the same RPM, right? That's a basic. We've got 4 different types of turbines. We have a turbojet, we have a turbofan that is used in the airlines primarily, we have a turboshaft that drives a helicopter or a boat or a tank or something, and then we have a turboprop, all right? But there's some things that all engines have in common, all right? So let's start with that. The question comes up, what are the 2 basic sections of a turbine engine? Well, the 2 basic sections are the cold section and the hot section, all right? So let's just stay with that. That'll be constant with any type of turbine. Another question comes up that says, what are the 3 main sections of a turbine engine? Now, even though there are other sections, the 3 main sections in the order that they operate are the compressor, the combustor, and the turbine, all right? So that's the same. Now let's talk about the inlet for a minute. Okay, most engines have got what they call inlet guide vanes. These are vanes that are in front of the first stage of compression, and if they are fixed, they are simply referred to as inlet guide vanes, all right? If they are variable, which I'm not sure if you can see this, see how they kind of move in and out? If they are variable, they are considered variable inlet guide vanes, and the advantage to that is that it helps the engine start, directing the air at the optimum angle. It also works in conjunction with the bleed valve that would be open during start to unload the compressor during starting, because we want the compressor to spool up as quickly as possible, all right? So inlet guide vanes or IGVs, variable inlet guide vanes or VIGVs, okay? Now, there are 2 types of compressor. This compressor happens to be an axial compressor, all right? So one stage of compression on an axial compressor is made of a rotor and a stator, all right? That is one stage of compression, all right? Now, most engines utilize several stages of compression, and when they're all mounted on the same shaft, this group of compressors is referred to as a spool, okay? So there's a spool. Now, let's talk a little bit about the compressor. So this is an axial compressor, all right? Remember, one stage of compression is a rotor and a stator. The stators happen to be of a divergent design, which is going outwards. The purpose of a divergent design is to slow down velocity and increase pressure and temperature, all right? So the stators in between each stage are a divergent design. Now, talk about compression ratio for a minute. Compression ratio is the difference between the air pressure coming into the first stage of compression versus the outlet of a compressor spool or a compressor assembly. This is considered the compression ratio, all right? Now, there is another kind of compressor. This is an impeller, and this is utilized in a centrifugal or centrifugal compressor, all right? Now, one stage of compression using an impeller or a centrifugal is an impeller and a diffuser, not a rotor and a stator, a impeller and a diffuser, all right? So just kind of keep that on the side. Air is compressed here and accelerates it outwards. All right, that's how the FAA describes that in a question, and that is a fact, right? Now, one thing about this compressor is that by itself, it does have a single stage, it does have the capability of producing a higher compression ratio than a single stage on the axial. However, you're limited to just two impellers or two centrifugal compressors per engine, and therefore then after that the disadvantages start to outweigh the advantages, and so that is why the axial compressor is by far the most popular compressor. Now, on turboshaft engines that are used, say, in helicopters, where the product is not thrust but torque or shaft horsepower, a lot of times they will use axial compressors and then a centrifugal compressor at the last stage. We're not going to get into some heavy detail on this. This is just a general discussion, all right? So, one stage of compression is a rotor and a stator in an axial. The stators are divergent. One stage of compression on a impeller or centrifugal is an impeller and a diffuser, all right? So, staying on the axial, then basically, like I said, these are by far the most popular type of compressors. Turbofans nowadays very often use two spools that are independent from each other, and some engines use three spools, all right? So, as we move down here, we already said that the compression ratio is the difference between the inlet and the outlet. Now, as we get to the outlet of the compressor, what's interesting about this is that this is the highest pressure point in the engine. Remember, the turbine engine is based on a constant pressure cycle, which is named after a gentleman named Brayton. So, unlike the recip engines, which operate on the Otto cycle, this is operated on the Brayton cycle. All right, constant pressure cycle is Brayton cycle, same, okay? So, we move down to this component here, all right? We already said the main components are the compressor, the combustor, and the turbine. But this little guy right here in the middle is very important, right? This is a diffuser, and the diffuser is also a divergent design. And why it is a divergent design is because as the air accelerates, we want to slow it down and convert velocity to pressure in order to slow it down to support combustion once it enters the combustion chamber, all right? Now, this engine, we have fuel nozzles installed here, so when this air is sent back, it mixes with the fuel. We would have igniters located on this component, and we would mix the fuel, air, and the spark in order to get combustion. Once the combustion has started and the engine has reached the point called self-sustaining, that's where the engine is capable of running by itself without any additional source of ignition. That is referred to as self-sustaining, and that happens at approximately 50% RPM. By the way, engine RPM is rated in percent and not in actual RPM. Okay? Now, one more thing on these axial blades. I'm just going to throw this in, seeing I'm making the video. We have a type of compressor blade that is referred to as a profile blade. That is the name of it. A profile blade has a very thin tip, the outer tip. The tip clearances here between the case and the compressor blade is very small, so somebody had the good idea to make the tips extremely thin. In the event that the tips actually contact the case, the damage would be negligible in most cases, all right? So remember, what is a profile blade on an axial compressor? It is a blade that is thinner at the tip, or you might be asked, what is a compressor blade that is thinner at the tip? And that is a profile type blade. So we move past the diffuser, which is a divergent duct, and now we slow it down before we introduce it. Now, an interesting fact is the air is pumping in here, but out of the 100% air that is coming into this engine, only about, just use general numbers, about 15 to 25% actually goes into this combustion chamber liner and supports combustion. The other, let's say 75 to 85%, surrounds this and adds in cooling. Okay, so not all the air coming through is used for combustion. That's a test question, and that's also a very important thing to know. Okay, the combustion liner or the combustion section has some constants. It doesn't matter on the type of engine. First of all, it's going to have a case, right? See the case down here? This is a cutaway, so this has been removed. The other thing is that it has perforations and louvers, and the idea on that is that the flame never actually touches this metal due to the technology involved in making these. And so the remaining 80–85%, whatever it is used for cooling. And of course, you know, we use the compressor discharge air. We send it off into different areas. It's known as a bleed air. And the bleed air does a lot of uses. It can provide anti-ice on a turbine engine. It can help with pressurization of the cabin. It could cross-start another engine on a turbofan situation. So basically, it's a good resource. The bleed air, we use bleed air a lot as a mechanism to activate other things. Okay, something else that all combustion chambers must have. They must have a source of ignition, right? Now this has been removed, but there would be an igniter here, right? Now different engines use a different number of igniters, just like they use a different number of fuel nozzles. But when you get to your FAA question, they're going to ask how many igniters are common on a turbine engine. When you see that question, you want to pick 2, all right? The FAA goes with that answer, 2 igniters per combustion. In reality, some engines have more, a few engines have less. They have 1, but FAA says 2, so stick with that. This combustion liner happens to be a axial flow, which means it is just a radial complete, sort of like a donut. Air comes in, combusts, and moves backwards. Okay? I'm not going to go into the different types of combustion chambers in this video. That's something that you can see on your PowerPoints and in class discussion. Okay, so as we move down the line, we hit this part right here. So we've left the combustion area and we're coming into the turbine area, right? So the first thing that this fire sees, this is referred to as a turbine nozzle, right? Sometimes the FAA refers to it as a stator because the blades are stationary, and but it is actually a nozzle because it does have a specific flow area, right? So the turbine nozzle is actually a convergent design because now we do want to increase speed and reduce pressure. And what they do is, okay, so it's the hottest point in the engine, so it's referred to also as the critical location in the engine because temperatures back here can range extremely high, let's say 1700, 1800 degrees Celsius, right? So if we were to exceed that temperature, then we would damage this nozzle. So everything is built around the heat capability of this first stage nozzle. Okay, that's very important. So this is the actual highest temperature point in the engine. Test question. What is the highest temperature point in this engine? It is the first stage turbine nozzle. Might be referred to as a first stage turbine inlet nozzle. A couple of different ways to describe it. Now, as we come back here, so now the gases and also the angle of the vanes that are on the nozzle, they are not only changing pressure and velocity, but they're angled in a way that they're going to strike the turbine blades at the optimum angle in order to get these most efficient. Now, we do have a nozzle in between each rotor stage, each turbine stage, just the way we did have a stator in between each compressor stage, all right? And so some engines just utilize 1 turbine Some use multiple because the exhaust gases are going past, so it's a good way to extract more energy. Now you're going to hear a question, and I want you to get this from the word go, right? What is the primary purpose of the turbine? The primary purpose is to drive the compressor. Because remember, once we reach self-sustaining and the engine is running by itself, there's no more ignition. So basically, the engine is running on its own. As long as it has a fuel supply and there's proper airflow coming through the engine, then it will continue to operate. So as the air strikes this is attached either mechanically or aerodynamically to the compressor. So the primary job on the compressor, on the turbine, is to drive the compressor. All right. One thing I forgot to mention, on the 6 o'clock position, on all combustor sections, there will be a drain valve. The drain valve is very important. When an aircraft is shut off, because the fuel pump is geared to the compressor side, as long as the compressor is spooling down, getting slower and slower, we're still pumping fuel into this engine. So when the pressure finally reduces after we've shut the engine off, the compressor, the combustor dump valve or drain valve will open, and any excess fuel will dump either overboard on older aircraft, or it'll be recycled in back to the fuel tank on more modern aircraft. All right. This is a very important component. If the dump valve is stuck closed, then when we shut this engine down, we will have a pool of fuel in there. So one characteristic is that I shut the engine down and I notice that the temperature rating is going up instead of down. That means that this fuel inside here is burning. The procedure there, it's not a dangerous situation. The pilot catches it. Basically, he would turn the fuel off, he would hit the starter button, and he would just simply rotate the compressor to blow air through here to help evaporate and blow out that residual fuel, right? If he did not do that, and he got back into the aircraft and there was a pool of unburned fuel in this combustion chamber, then the next start could very well be a hot start. A hot start, by the way, by definition, is anytime the max temperature limits are exceeded during start, that is considered a hot start. There's another type of start that you'll see in your quizzes and on the finals, and that is what is a hung start. A hung start is when the engine starts normally, everything looks good, but as we start to advance fuel, RPM does not increase. It's hanging up. We're probably going to see an increase in temperature because we're dumping more fuel in there, but we're not getting more RPM, so we're not pumping any more air through there, right? So that is a hung start. In both cases, the hot start or the hung start, that is a mechanical issue. It has to be reported to your maintenance team, and that has to be resolved. They have to find the cause of that. Okay, as we get back to the exhaust section, I'm going to try to keep it simple. This engine utilizes what's called an EGT system, which stands for exhaust gas temperature. Now, we said that the first stage turbine nozzle is actually the hottest point in the engine. So, some manufacturers choose to put their temperature probes here, in which case it would not be called the EGT, the exhaust gas temperature, but it would be called the TIT, or the turbine inlet temperature. Now, this is very common, but you have to remember the temperature up here is very, very high. Like I said, 17,800, 1,800 degrees Celsius. So, therefore, the probes would be under a much more hostile environment. They would be much more expensive. They would probably need to be replaced more often. What a lot of manufacturers do is they use a EGT system, which basically, if this is running at 1,700 degrees Celsius, by the time we get to the exhaust, this might be down around 600 or 650 degrees Celsius. So that's just kind of a way to monitor temperature without exposing these probes to a very, very high temperature. All right. Now the exhaust, the EGT probes, or exhaust gas temperature probes, you can see that there is a harness here. When these are replaced, the entire harness has to be replaced. There is no way to replace individual probes, not in this system, and there is no repairs authorized. You can't splice this together in any way, all right? So EGT, exhaust gas temperature, or TIT would be turbine inlet temperature, all right? Now let's talk for a minute, seeing as I got your attention, hopefully, right? So on the turbine blades, we're going to talk about a couple of things real quick, and they'll make more sense to you as we go along in the class, right? A couple of things happen. This has an open tip blade, which is fine, and some blades utilize, let me get this apart. Some turbines utilize a blade that has a shroud on the outer part. So if you were to put those all together and to make a complete disc, you would see that they're shrouded, right? So the primary advantage to a shrouded blade is that it does prevent vibration. These do move a little bit, and with the shrouding, it helps to prevent excessive vibration. Also, there's an aerodynamic quality as these knife edges on the tips, they ride inside of a channel, and they make the blade a bit more efficient. Now, like everything else, there's a upside and a downside, right? When a turbine blade increases in length permanently, because remember, this is exposed to a very high temperature and very high RPM, when that, the permanent elongation of a turbine blade is referred to as creep, all right? Okay, we want to remember that, creep. So, you can imagine that with this extra mass at the end of the blade pulling centrifugally, this blade would be more subject to stretch because of this weight on the end of it, right? So, when this engine is on the drawing board and is being designed, turbine blades that have an open tip, they might be utilized in a turbine that runs at higher RPM. Now, all turbines run at a higher RPM, but just to throw some numbers out here, these open tips might be quite suitable for a turbine that's running at, say, 45,000 RPM. And if they decide to go with a shrouded type of blade, then because of the extra weight here, they would use this on an engine that was designed to run at a slightly lower RPM, let's say 30 or 35,000 RPM. All right? So the other thing is, we haven't covered this in class yet, but there's more to know about this, right? These blades come in different designs. So the three types of turbine blades, and you'll see this in your quizzes, and it will be part of the class, is they have an impulse blade, which were used early on, and they have a shape sort of like a bucket, all right? And then later they came up with an aerodynamic blade, which resembled more of a compressor blade. It just looked like an aerodynamic blade profile, right? Then they realized that both characteristics had an advantage. So they combined the two, and so they have, and that's referred to as a, I'm sorry, the first type, the bucket type, is called impulse. The second type, which is more aerodynamic, is called reaction. And then the combination of the two is called impulse reaction. That is the most commonly used today, right? So there's a test question for you as well, okay? So, on exhaust sections, on subsonic aircraft, right? Very specific there, right? You can see that the shape of the exhaust nozzle in conjunction with this exhaust cone, or jet nozzle, or jet cone, it forms a convergent design because we now, as we said, the divergent decreases velocity and increases pressure. Now we're trying to produce thrust, so the convergent characteristics actually decreases pressure and increases velocity. And that's what we're all about. That's what we want to do. So the only exception to that is supersonic aircraft, mostly military aircraft, all right? There's a couple of things you need to know about that. First of all aircraft, as they're flying, whether they're flying sub-Mach or supersonic, the inlet design has to be such where the air entering the engine must be below Mach 1. That's an absolute, right? The engine cannot support air coming into it. Now, they do that through the inlet design or something that's called variable geometry on the inlet design, which means that the inlet might actually change in shape mechanically to adjust to different speeds. Now, the exhaust is always convergent on subsonic aircraft. However, when we get into supersonic aircraft, the exhaust has to be convergent and then divergent, right? There's no easy way to explain that other than the fact that at Mach speeds, a traditional convergent exhaust, that will actually start to choke off or block itself because it can't handle that type of acceleration. So they have to open that up. So supersonic aircraft use a convergent, divergent design, all right? So, like I said, I wanted to keep this kind of brief. One thing I wanted to talk about too, because this is hard information. This is a relatively small turbofan that is used in a low bypass turbofan engine, right? These little fins on the side have a name. Oh, something that I forgot to mention. So we talked about creep, right? When creep occurs and damage happens to the compressor case and the blade, that phenomena is called galling. The actual damage is called galling. So that's another test question, and that's something that you need to be aware of, all right? So we have galling there, all right? Let's see if I forgot anything on that. No, okay. And if you do a hot section inspection, which means you're looking back here and you see a waviness to the nozzle or to the blades, the wavy type of damage is normally caused by overheat, over temperature, right? So now, back into the turbofan. So these items right here are called a mid-span shroud, all right? It's a mid-span shroud. They stiffen the blade, and they also help to channel the air in the direction that it is intended to go. So sometimes because these go around the entire inlet, these touch each other, so they have a tendency to wear. So when these wear or they overlap, then that damage is referred to as a shingling, all right? So we have a lot of words to remember, but mid-span shroud, because remember, this is nothing more than an airfoil, right? So we have a span, and we have a cord, all right? So even though it's not exactly in the middle, or they might even be more than one, they're all referred to as a mid-span shroud, okay? Remember that. Now, on the mounting side here, now that I get into this, there's different ways to mount blades, whether it's turbine blades, fan blades, or compressor blades, right? This is known as a dovetail attachment. As you can see, it kind of like resembles a dovetail, all right? Now, on turbine blades, by far the most common, and this is the FAA's favorite, is you can see where these blades are inserted into this disc. If you think about it, these kind of resemble a little Christmas tree upside down. So these are referred to as fir tree attachment, fir, F-I-R, all right? Not fig tree or not plum tree, not Christmas tree, right? These are fir tree attachments. And the reason for these is because it has the most surface area to secure the blade in there. Now this stops the blade from flinging out with high centrifugal loads, and then there would be rivets or the blades would be peened in order to keep them from moving axially, okay? So that's what's going on there. We have the fir tree attachment. It is by far the most common attachment process that's used in turbine blades and also many of the compressor blades as well. So the FAA's favorite is fir tree attachment, all right? I think that is all I wanted to cover. I didn't want to get in too much detail. Quick review on bearings. Two main types. Let me just get this engine out of the way. Just talk to you for a minute. The two main types of bearings that are used in the turbine engine are ball which are used for axial loads or thrust loads, or roller bearings, which are used for radial loads or centering loads, right? Here's an example of a roller bearing, right? And then I don't have a ball bearing handy, but ball bearing and roller bearing, all right? And then I don't have something to show you right now, but it's in the study material. The two basic types of seals are called labyrinth seal and carbon contact. Now, the carbon contact seals are easy to understand. They have a carbon ring that actually contacts the item that is sealing. Because remember, the bearings are being lubricated, so we have to stop the oil from leaving that bearing cavity, right? So a carbon contact seal actually touches what it's sealing. A labyrinth seal is a little different. It doesn't actually touch the item that it's sealing, but it comes very, very close to the item. A labyrinth is something that has a bit of a maze to it, not a straight through. Question comes up, how does a labyrinth seal work? What they do is they put bleed air into the seal, and it is pumped in, and it forms a boundary layer between the seal and the rotating shaft, and it prevents the oil from coming out. So two types of bearings are ball and roller. Two types of seal are carbon contact and labyrinth seal, all right? Let's talk real quickly about two other items, and then I'll close this off. Let's talk about thrust reversers, okay? Thrust reversers come in two basic designs. One is a mechanical blockage, and what that is basically clamshell doors come out. These are used on turbofan engines. Clamshell doors come out and they block the air coming from the fan and the exhaust gases, total. Those are aerodynamic blockage, and they move it forward, all right? The other type is called aerodynamic blockage, and what that does is we have a door that opens up on the side of the engine cowling, and it only uses fan air, which is providing the majority of the thrust, and it diverts that forward, all right? So aerodynamic blockage using fan air only, mechanical blockage, clamshell doors come before the, after the exhaust and the fan discharge air totally. So why do we use thrust reversers? Well, obviously we want to stop the aircraft sooner, but something that a lot of people don't think about is the fact that thrust reversers also take a lot of the load off of the brakes. If an aircraft did not have thrust reversers, then it would depend solely on the brakes to stop the aircraft. The brakes would become extremely hot, which would increase maintenance, and also it could prevent turnaround time as far as the aircraft landing and then taking off again. It's going to cause maintenance problems. So something that a lot of people don't think about. But yes, the thrust reverser does stop the aircraft sooner, but think of what that does to the brakes, right? It really keeps the brakes a lot cooler, okay? We're going to talk about real quick before I disconnect, afterburners, all right? So afterburners, the way they work on military aircraft is they take the air that has already been burned, it still has air molecules in that exhaust, they pump in additional fuel, they relight it with another set of igniters, and then we get that sudden burst of speed that we've all seen in Top Gun and all these military movies, right? This is a great design. It's been around a long time. The parts that are involved in there is that we have to have a fuel source, which are either fuel nozzles or sometimes called a fuel rail. And the other thing it needs is a source of ignition. Then there's a thing that goes up inside, which it's better to show you than to talk about it, but it's called a flame holder. It's just a big piece of thick metal that kind of goes about halfway up, and that just sets up a little back pressure, right? And now the afterburners are capable of accelerating the aircraft 100 times faster, 100% faster than its original speed, but for only short periods of time. It utilizes its own fuel control because we still need the main engine to be running normally. We don't want to rob the fuel from the main engine. So it has its own separate fuel control that sends its own fuel source, and it can only be used for short bursts of time. or else simply the aircraft would just run out of fuel. Also, it's extremely hot, so it does cause some damage to the exhaust section, all right? So that's thrust reversers. Another thing on fighter aircraft is when the tail of the aircraft actually, the tailpipe actually moves up or down, left or right, that is called thrust vectoring, right? This is normally for combat maneuvers. They want to make a sharper turn, so the exhaust pipe, for lack of a better word, will turn a little bit left or right, up or down, in order to assist in that type of a maneuver. Okay, I'm sure I'm leaving some things out, but like I said, this was intended to just be a overall. The video that I put together yesterday didn't come out very well. So I hope that answers a lot of questions. I'm going to work on now getting this video posted. So thank you very much for joining, and keep those quizzes coming in every day, and I will talk to you soon. Okay, Mr. G out.